Within the next decade, humanity will likely discover extraterrestrial life, and 3 separate missions are already searching in places we know it could exist. This isn't speculation. This isn't optimistic science fiction. For the first time in history, we have spacecraft capable of directly sampling alien oceans, telescopes sensitive enough to smell life in distant atmospheres, and technology powerful enough to detect artificial signals from civilizations thousands of light years away. By the end of this, you'll understand exactly why astrobiologists are more confident than ever that the answer to "Are we alone?" is about to change from mystery to discovery, and why that discovery might happen far sooner than you think. To understand why we're on the verge of this breakthrough, you need to know what changed. For most of human history, searching for alien life meant scanning radio signals and hoping someone out there was broadcasting. That was it. A cosmic waiting game. But in the last decade, 3 revolutionary shifts occurred. 1. We discovered that planets are everywhere. Nearly every star has them. 2. We built instruments that can analyze the atmospheres of those planets for chemical signs of life. 3. We found oceans, liquid water oceans, right here in our solar system, on moons we can actually reach. Here's the thing, we're no longer searching blind. We know where to look, we know what to look for, and we have the tools to do it. Now, let's break down exactly how each pathway could deliver the answer. The James Webb Space Telescope isn't just taking pretty pictures of distant galaxies. It's performing a far more profound task, sniffing the air of alien worlds. When an exoplanet passes in front of its star, an event called a transit, starlight filters through the planet's atmosphere before reaching us. Different molecules absorb different wavelengths of that light, leaving chemical fingerprints. Think of it like this. If you shine a flashlight through colored glass, the glass absorbs certain colors and lets others through. By analyzing which colors are missing from the starlight, we can tell what gases are in that planet's atmosphere. Oxygen, methane, water vapor, carbon dioxide, and, crucially, combinations of gases that shouldn't exist together unless something is actively producing them. Now pay attention to this. On Earth, oxygen and methane coexist in our atmosphere, but they react with each other chemically. Without constant replenishment, they disappear in geological eye blinks. So what replenishes them? Life. Plants produce oxygen, bacteria in wetlands and cow guts produce methane. If we detect both in significant quantities on an exoplanet, it's a massive red flag pointing toward biology. Get this, in September 2023, JWST detected methane and carbon dioxide in the atmosphere of K2-18b, a planet 120 light-years away in the habitable zone of its star. K2-18b is about 8.6 times Earth's mass, likely covered in oceans beneath a hydrogen-rich atmosphere, a type of world called a Hycean planet. But here's where it gets crazy. JWST also detected a tentative signal of dimethyl sulfide, or DMS. Here's the thing. On Earth, DMS is almost exclusively produced by ocean phytoplankton. We know of no significant non-biological sources. It's one of the strongest biosignature molecules we could hope to find. Most people don't realize this, but the detection is still tentative. The signal is faint and needs confirmation. Follow-up observations are scheduled for 2024 and 2025. If confirmed, K2-18b becomes the first planet beyond our solar system with strong evidence of biological activity. Not proof, not yet, but evidence strong enough to redirect every major telescope toward it. The truth is, we might already be looking at an inhabited world, but Webb isn't our only shot, because there's a place much closer to home where life might be thriving right now, and we're sending a robot to find it. In October 2024, NASA launched the Europa Clipper mission. Its destination, Jupiter's moon Europa, one of the most promising places in the solar system to find life. Europa is slightly smaller than Earth's moon, but beneath its frozen surface lies a global ocean of liquid water, more water than all of Earth's oceans combined. Think about it. Europa has 3 key ingredients for life. Liquid water, check. Chemical energy from interactions between the ocean and the rocky seafloor. Check. And organic molecules delivered by comets and asteroids over billions of years. Check. Now, Europa's ocean is kept liquid not by sunlight. Jupiter is far too cold for that, but by tidal heating. Jupiter's immense gravity squeezes and stretches Europa as it orbits, generating internal friction and heat. The same process keeps Earth's interior molten. But here's the catch. The ocean is buried under 10 to 15 kilometers of ice. We can't drill through that, not yet. So how do we sample the ocean? Get this, Europa has geysers, plumes of water vapor erupting from cracks in the ice, shooting hundreds of kilometers into space before falling back down as snow. The Clipper spacecraft will fly through those plumes, collecting samples with onboard instruments designed to detect organic molecules, salts, and potential biosignatures. It's like sticking a test tube into an alien ocean without ever landing. Scientists were shocked to discover that Europa's plumes might be connected directly to the subsurface ocean, meaning we could be sampling pristine ocean water without any contamination from surface ice. Now pay attention to this. Clipper carries 9 science instruments, including a mass spectrometer to identify molecules in the plumes, ice-penetrating radar to map the thickness of the ice shell and confirm the ocean's existence, and cameras capable of imaging the surface at resolutions down to 50 centimeters per pixel. If there's life in Europa's ocean, even microbial life, Clipper has a real chance of detecting chemical evidence of it. And here's what nobody talks about. Europa isn't alone. Saturn's moon Enceladus also has a subsurface ocean and active plumes. NASA's Cassini spacecraft flew through Enceladus's plumes in 2015 and detected molecular hydrogen, a sign of hydrothermal vents on the ocean floor. Hydrothermal vents on Earth are surrounded by thriving ecosystems that don't rely on sunlight, life powered entirely by chemical energy from the vents. If the same process is happening on Enceladus or Europa, we could find life completely independent of the sun. The truth is, our solar system might host multiple biospheres, and we're finally going to check. But what if life out there isn't hiding under ice or in distant atmospheres? What if it's technological and trying to contact us? For over 60 years, SETI, the search for extraterrestrial intelligence, has been scanning the skies for radio signals from alien civilizations. And for 60 years, the silence has been deafening. But here's the thing. SETI has only scratched the surface of what's possible. Until recently, we lacked the computing power and telescope sensitivity to conduct truly comprehensive searches. That's changing. Fast. Breakthrough. LISTEN, launched in 2015 with $100 million in funding, is the most powerful SETI program ever conceived. It's surveying 1 million nearby stars, scanning the entire galactic plane, and listening to 100 nearby galaxies for signals across billions of radio frequencies. Get this. Breakthrough. LISTEN generates so much data that it took years just to build the AI systems to process it all. Now, we're not just listening for deliberate broadcasts anymore. We're looking for technosignatures, any evidence of technology, intentional or not. Radio leakage from alien communication networks, laser pulses used for interstellar messaging, waste heat from megastructures harvesting stellar energy. Think about it. Earth has been leaking radio signals into space for over a century. If another civilization is doing the same, and if they're close enough, we could detect it. Most people don't realize this, but in 2023, researchers analyzed data from the Parkes Radio Telescope in Australia and found a narrow-band signal coming from the direction of Proxima Centauri, the closest star system to Earth, just 4.2 light-years away. The signal, dubbed BLC-1, Breakthrough Listen Candidate 1, had several characteristics consistent with an artificial transmission. It was narrow-band, meaning it occupied a very specific frequency, something natural astrophysical sources almost never do. It appeared to shift in frequency over time, consistent with motion from a planet orbiting a star. And it only appeared when the telescope pointed at Proxima Centauri, disappearing when pointed elsewhere. But here's the catch. After exhaustive analysis, researchers determined BLC-1 was likely radio interference from human technology mimicking an alien signal. Disappointing? but instructive. Because the fact that we can detect such faint, narrow signals from nearby stars means we're genuinely capable of finding real technosignatures if they exist. Now pay attention to this. SETI is also expanding beyond radio. Optical SETI scans for brief laser pulses, flashes of light potentially used for interstellar communication. A sufficiently powerful laser pulse could briefly outshine its host star, making it detectable across dozens of light years. And here's where it gets really interesting. We're starting to search for industrial pollution in exoplanet atmospheres. Specifically, chlorofluorocarbons, CFCs. CFCs are synthetic chemicals that don't occur naturally. Humans created them for refrigeration and aerosols before realizing they destroyed the ozone layer and banning them in the 1980s. But an alien civilization might not have banned them yet, or might use them intentionally for terraforming or industrial purposes. Get this, JWST is sensitive enough to detect CFCs in the atmosphere of a planet dozens of light years away, if present in sufficient concentrations. Scientists were shocked to discover that we could potentially detect not just life, but industrial civilizations through atmospheric spectroscopy. The truth is, we're no longer just passively listening. We're actively hunting for every possible sign of intelligence, from radio whispers to chemical fingerprints of factories. But there's a fourth approach that's even more direct, and it's producing results that no one saw coming. Here's what nobody talks about in mainstream astrobiology. The U.S. government has officially acknowledged the existence of unidentified aerial phenomena, UAPs, that display flight characteristics beyond known human technology. In 2020 and 2021, the Pentagon released videos recorded by Navy pilots showing objects performing maneuvers that seem to defy physics: instantaneous acceleration, hypersonic speeds without sonic booms, trans-medium travel between air and water. Now, this doesn't mean these are alien spacecraft. The default scientific position is skepticism. They could be sensor artifacts, atmospheric phenomena, or classified human technology. But here's the thing. In June 2021, the Office of the Director of National Intelligence released an unclassified report admitting that out of 144 UAP encounters analyzed, 143 remain unexplained. In 2022, NASA commissioned an independent study team to examine UAPs from a scientific perspective. And in 2023, Congress held public hearings where military whistleblowers testified under oath about alleged recovery programs for non-human technology. Get this. Whether you believe these claims or not, the fact that credible institutions are taking them seriously represents a shift. UAP research is moving from fringe conspiracy theory to legitimate scientific inquiry. Now pay attention to this. NASA's UAP study concluded that while most sightings can be explained by mundane phenomena, a small percentage exhibit characteristics that warrant further investigation with rigorous scientific methods. They recommended deploying calibrated sensor networks specifically designed to gather high-quality data on UAPs. Think about it. If even one of these objects turns out to be of non-human origin, it would be the most significant discovery in human history. Not distant radio signals, not microbes under ice, but physical evidence of advanced technology here in Earth's atmosphere. Most people don't realize this, but the scientific community is now cautiously open to investigating this possibility, not as a certainty, but as a hypothesis worth testing. The truth is, the search for alien life isn't just telescopes and spacecraft anymore. It's also sensor networks, data analysis, and a willingness to take seriously phenomena we don't yet understand. And all of these approaches are converging on the same critical decade, because the timeline for potential discovery is shockingly short. Before we go further, I need to tell you something that ties all of this together. Here's what they didn't tell you in the headlines. These aren't isolated efforts happening in parallel. They're coordinated. JWST is prioritizing observations of exoplanets flagged by ground-based surveys as the most likely to harbor life. Europa Clipper's findings will inform future missions to Enceladus and potentially Titan. And data from SETI initiatives is being cross-referenced with exoplanet catalogs to target stars with confirmed habitable zone planets. What does this mean? It means we're not just throwing darts at the universe, hoping to get lucky. We're systematically narrowing the search, focusing resources on the highest probability targets. By 2030, Europa Clipper will have completed its primary mission, nearly 50 flybys of Europa, some as close as 25 kilometers above the surface. If life exists in Europa's ocean and leaves chemical traces in the plumes, we'll know. By 2035, JWST will have observed hundreds of exoplanets, building a statistical sample large enough to determine how common biosignature gases are. One or two detections could be flukes. Dozens would suggest life is widespread. And here's where it gets crazy. Ground-based telescopes are also getting massive upgrades. The extremely large telescope ELT in Chile with a 39-meter mirror will come online in 2028. It will be able to directly image exoplanets, not just infer their existence from wobbles or shadows, but actually see them as distinct points of light. Get this, the ELT will have enough resolution to map weather patterns, detect seasonal changes, and analyze atmospheres in far greater detail than JWST. Now pay attention to this. If we detect oxygen in an exoplanet's atmosphere using JWST, the ELT can follow up by looking for chlorophyll, the pigment plants use for photosynthesis. Chlorophyll has a distinctive spectral signature called the red edge. On Earth, vegetation reflects near-infrared light strongly, creating a sharp spike in the spectrum. If we see that on another world, it's not proof of life, but it's damn close. Scientists were shocked to discover that we're not decades away from this capability. We're years away. And here's the kicker. Multiple missions and telescopes reaching maturity in the same decade means redundancy. If one method fails or produces ambiguous results, others might succeed. The truth is, the convergence of technologies, missions, and data in the 2030s creates a window of opportunity unlike anything in history. But what happens if we actually find it? That's where the story gets complicated. Let's play this out. Imagine it's 2032. JWST has confirmed dimethyl sulfide, oxygen, and methane in the atmosphere of K2-18b. Independent observations from the ELT corroborate the findings. The data is peer-reviewed, replicated, and released to the world. Humanity's reaction would be complicated. Think about it. We wouldn't be meeting aliens. We'd be detecting chemical evidence of microbial life on a world 120 light-years away. No contact, no communication, just the knowledge that biology exists elsewhere. Here's the thing. That knowledge alone would be transformative. Religions would grapple with the implications for doctrines of creation and humanity's place in the cosmos. Some would see it as confirmation that life is God's design scaled universally. Others might face theological crisis. Philosophers would revisit existential questions. If life is common, what makes us special? Does consciousness still matter if it emerges everywhere? Scientists would immediately pivot. Every telescope would point at K2-18b. Funding for astrobiology would skyrocket. Missions to Europa and Enceladus would be fast-tracked. But here's the catch. We'd also face frustration. Because 120 light-years is impossibly far. A radio signal would take 120 years to reach them, and another 120 to hear a reply. Physical travel, with current technology, would take hundreds of thousands of years. Get this. We'd know life is there, but we couldn't touch it, talk to it, or visit it in any time frame that matters to living humans. Now, contrast that with finding life on Europa. If Clipper detects organic molecules, amino acids, or, best case, actual microbial cells in Europa's plumes, the response would be different. Europa is here, in our solar system, reachable. We could send landers, submarines, maybe even human explorers within our lifetimes. And this is the part that changes everything. If life arose independently on Europa, it means the genesis of life isn't a one-time fluke. It happened at least twice in the same star system. Most people don't realize this, but that would make life statistically ubiquitous. If 2 out of 8 planets in our solar system host biospheres, the galaxy likely contains billions of living worlds. The truth is, the implications aren't just scientific. They're philosophical, political, spiritual. If we find Life. We immediately become a species that knows it's not alone, even if we're still isolated. And that psychological shift would ripple through every aspect of human culture. But wait, there's more. What if the discovery isn't microbial? What if SETI detects a deliberate signal? Then everything accelerates, because a signal means intelligence, technology, possibly a message. If we receive a confirmed technosignature, a radio signal, a laser pulse, atmospheric pollution, what happens next? First, verification. Independent teams would analyze the data to rule out interference, natural sources, or errors. This could take months or years. Second, the decision to respond. Here's what nobody talks about. Humanity has no unified protocol for replying to an alien signal. SETI researchers have drafted guidelines, suggesting that any response should be a collective human decision, not made by one country or organization. But in practice, enforcement is impossible. Anyone with a powerful transmitter could send a message. Think about it. Do we respond at all? Some scientists, like Stephen Hawking, warned against revealing our location to unknown civilizations. What if contact invites danger? Others argue that if a civilization can already detect us, and we can detect them, then mutual awareness is inevitable. Silence is pointless. Get this. If the signal comes from a star 1,000 light-years away, any message we send wouldn't arrive for 1,000 years, and a reply would take another 1,000. That's a 2,000-year conversation lag. Civilizations rise and fall in that time. Now pay attention to this. The content of the message matters. Do we send mathematics, art, a greeting, a warning? In 1974, the Arecibo radio telescope sent a message toward the globular cluster M13. It contained basic information about humanity, our solar system, and DNA structure, but some criticized it as presumptuous, speaking for all humanity without consensus. The truth is, first contact, if it happens, will force humanity to confront questions we've avoided. Who represents us? What do we say? And are we ready for the answers they might give? But here's the catch. Even without contact, just knowing intelligent life exists out there would change us. It would make our conflicts seem smaller, our planet more precious. It might unify us or divide us further over how to respond. What does this mean? It means the search for alien life isn't just about discovery. It's about deciding who we want to be when we're no longer alone. So here's where we stand. We have the tools, we have the targets, and we have the timeline. Within the next 10 to 15 years, one of these methods will likely deliver an answer. Maybe it's a whiff of dimethyl sulfide in an alien sky. Maybe it's amino acids in an icy plume. Maybe it's a repeating radio pulse that can't be explained any other way. But the answer is coming, and when it does, everything changes.